So today we're going to be focusing on proving the famous identity e to the I pi plus 1 equals 0. And this is attributed to Leonhard Euler. And it's beautiful in itself that it contains like very famous math constants like e, which is Euler's number. So e is approximately 2.71 and so on and so forth. This is the base. This is really ugly, e, sorry. This is the base of the natural logarithm, which you may have encountered. And then, of course, we have pi, which is approximately equal to 3.1415, and so on and so forth. And this represents the ratio between the length of a circle and its diameter, which always turns out to be this number. And last but not least, we have I. I represents the imaginary unit, which, if you square it, gives you -1. And it's beautiful that all of these famous constants have come together in this very beautiful equation, and this is exactly why I want to prove it today. And the main ingredient that we're going to be using today is the Taylor series of a function. Namely, that for sufficiently nice functions, you can write f of x, you can express it at least around the small neighborhood of a point in terms of an infinite series. So in other words, at least for some sufficiently small set, f of x can be expressed as an infinite sum with n going from 0 to infinity of an times some power of x minus a, where a is some real number. This is the Taylor series. This is some power series expansion of f centered around the point A. So Taylor series actually give us a way to compute these series expansions and actually to compute their coefficients. And moreover, it tells us that they are somehow related to the nth derivative of function f evaluated at some point. And of course, you have to divide it by n factorial. And in order to prove the Euler's identity, we're going to go over the following steps. So the steps that we're going to be going over today is finding the Taylor series for the function e to the x, cosine of x, and sine of x. And then, having found those Taylor series, we will be actually able to prove that e to the ix is equal to cosine of x plus I to the sine of x. So this is going to be the almost final goal which we have today. And yeah, so once we have this, the final result is going to be almost like instantaneous. All right, so in order to find the Taylor series for e to the x, let us first consider function f. This is of course going to be defined over the whole real numbers, and f of x is equal to e to the x. And so in order to find the Taylor series of a certain function, once again, you have to look at its derivatives. This is going to be like a very easy case, if not the easiest, but except, maybe the constant functions or polynomials. Because you can find the derivative of e to the x very easy. So recall that the derivative of e to the x is e to the x, so nothing changes. And once again, the second derivative of e to the x is, well, of course, you have to differentiate this, so it's also going to be e to the x. And this is true for all terms or derivatives higher order, meaning that the nth derivative of f is also going to be e to the x. And we're going to be focusing on a Taylor series centered at 0, meaning that this a will be 0, and we would actually get that, f of x, let's write it here very quickly, it's going to be equal to the sum from 0 to infinity of the nth derivative of f calculated in 0 over n factorial times x to the n. And this is perhaps the nicest form of a Taylor series, which is sometimes called a Maclaurin expansion or a Maclaurin series of f. And of course, we want to evaluate these derivatives in 0, but recall that e to the 0th power is just 1, meaning that for any n, we have that the nth derivative of f is just 1. And of course, this being true for any positive integer. So circling back, we get that e to the x is equal to the sum from n going to 0 to infinity of 1 over n factorial times x to the n. And this concludes the first part in proving the Euler's identity. So next we're going to want to look at the function f of x equals sine of x. And let's quickly rewrite the Taylor's formula, to remember what we have to do. So once again, we want to compute the nth derivative. And we have that the derivative of x is just cosine of x. And once again, we get that if we substitute 0 here, we have cosine of 0, and remember cosine of 0 is 1. And next we have the second derivative of x, which is just the derivative of cosine of x, but remember that derivative is equal to minus sine of x. And we would get that the second derivative of f evaluated in 0 is just sine of x evaluated in 0, which is 0. And next we have the third derivative of x, so maybe we're going for some sort of recurrence or some pattern which seems to be repeating, but we're not there yet. So the third derivative of x is going to be minus the derivative of sine, which, once again, the derivative of sine of x is cosine of x, so therefore this will be cosine of x. And this means that the third derivative of f in 0 will just be minus 1. And last, let's compute the fourth derivative of f. I will just use Roman letters here. And the derivative of cosine of x is minus sine of x, but notice we have a minus sign here again, so we would just get sine of x. So the fourth derivative of f evaluated in 0 will just be sine of 0, which is 0. Notice that the fourth derivative of f is just f. We seem to have found a repeating pattern. Every 4 times we differentiate f, we get the same thing. And also note that the second and fourth derivative are 0, and the first and third derivative of f are 1 and minus 1. And to get a better idea of how this infinite sum will look, let us actually express this term over here. So this would be f of 0 times over 0 factorial, which is just 1, plus x to the 0, which is 1. And then we will have that f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, triple prime of 0 over 3 factorial, x to the third power, and so on and so forth. We're running out of space. So we're going to be substituting these terms over here, the derivatives, with the values we've obtained over here. The f evaluated in 0 is just sine of 0, which is 0. And then we get derivative of f in 0 is 1, so we just get x. Then this term is also equal to 0 because the second derivative is 0. Then we get this guy over here is just a minus 1, so we get minus x to the third power over 3 factorial. The fourth term will also be 0 because the fourth derivative is 0, evaluated at 0. The fifth derivative of f would be 1, evaluated in 0, so we just get, this is x to the 5 power over 5 factorial, and then minus x to the 7 over 7 factorial, and so on and so forth. Alright, so this will actually be the Taylor expansion of the function sine of x. And once again, I have rewritten what we've discovered so far in order to be more accessible for us a bit later. So this is the expansion for e to the x, explicitly, and this is the expansion for sine to the x. And let's go over the last one, which will be the cosine of x. We'll proceed in a similar manner as we did with the sine of x, being very similar functions. So, f of x is equal to cosine of x, and the derivative of cosine of x, remember that, is just minus sine of x, and this means that the derivative of f evaluated in 0 is just 0, because sine of 0 is 0, and then we have that f double prime of x will be minus the derivative of x, which is minus cosine of x, and this would be, so f double prime of 0 is minus 1. And, it's also worth noting that if this is f of x, let's write it somewhere, I don't know, here, that f of 0 is also equal to 1. We'll need this term as well. Next, we get that f triple prime of x will be the derivative of this guy, which is just minus the derivative of cosine, so minus sine of x minus sine of x, which is just equal to sine of x. And therefore, we obtain that the third derivative of x evaluated at 0 is also 0. The last one, the fourth derivative of x, is the derivative of sine, which is just cosine of x. Once again, the fourth derivative of f evaluated at 0 is just going to be 1. And let's see what we have obtained. We have that the cosine of x is just going to be, so the first term is going to be, so for some reason I keep deleting the formula, so I'm just going to write it once again over here. So we need the f of 0, and then this is 0 factorial, this is x to the 0th power, so we'll just get a 1. Then the second term, for the second term we have the derivative equal to 0, so we'll just omit it. And let's look at the next term. So the second derivative of f is equal to minus 1, so we have minus 1 over 2 factorial, so we have 2 factorial from here, and this is x to the second power. So I'll just put x to the second power over here. And next, the third term of this expansion will also be equal to 0 because we have this derivative over here. And the fourth one will be equal to, so it's just 1 over 4 factorial, and we have x to the 4th power. And I'll just put it over here on the numerator. And this pattern seems to be continuing infinitely, so we have minus x to the 6th power over 6 factorial, and x to the 8th power over 7 factorial, and so on and so forth. And while this part is done, we are almost there, because now we're going to be proving the famous formula e to the ix is equal to the cosine of x plus I times the sine of x. And as a small remark, notice that these formulas are true for any x real number. So these formulas work for any real number x. The function which we have calculated over here are infinitely differentiable at any point in R. So let's go over proving this fact real quick. So we have that e to the power ix will just be equal to 1 plus ix plus ix squared over 2 factorial plus ix plus ix to the 3rd power over 3 factorial, and so on and so forth. And let's just actually let's express each of these terms over here. So we have that this is 1 plus ix, so nothing has changed so far, and then we have I to the 2nd power over here. So this would equate to a minus over here, and we're left with x squared over 2 factorial. And next we have I to the 3rd power over here, which remember that is just equal to minus. So I to the 2nd power is minus 1, and I to the 3rd power is just minus I. So this would give us minus I times x to the 3rd power over 3 factorial, and the next term would have been ix to the 4th power over 4 factorial. So I to the 4th power, also note that it's equal to 1, and therefore this term over here would be equal to x to the 4th power over 4. And now let us actually group the real part of this expression and the imaginary part of this expression. So we have 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial, and subsequent terms turn out to be x to the 6th power over 6 factorial, and so on and so forth. I'll maybe leave it up to you to check that the next term are indeed coming up like this. So also the next one would be x to the 8th power over 8 factorial, and so on. And now we can factor out an I from these imaginary terms, and we get that this is equal to I over, so we have an x from over here, and then we have a minus x to the 3rd power over 3 factorial, and the next term would have been, once again you can check it out, it's x to the 5th power over 5 factorial. And we can notice that using the Taylor expansion, which we have just calculated earlier, we can notice that the first one is just equal to the cosine of x, and then plus I times the sine of x. This is the sine of x as we have discussed over here. And therefore, e to the ix is equal to cosine of x plus I sine of x. So this is e to the ix. So once again, the goal was to prove Euler's formula, and in order to do that, we just have to substitute x equals pi, and let's see what we get. So if we substitute with x equal pi, we get that e to the I pi equals the cosine of pi plus I times the sine of pi. But remember that the cosine of pi is actually -1, so this term over here is just -1, and the sine of pi is sine of 180 degrees, which is 0. And we get that e to the I pi equals -1 plus 0, or in other words, we get that e to the I pi plus 1 equals 0. And this was exactly what we wanted to prove. Please consider subscribing to the channel if you want to see more stuff like this.